We have this density problem. There is all my work in my answers. If you just need to see that for part A, it gives us the derivative. And so you know to approximate a derivative, we're going to write down those 2 points in that vicinity. We're just going to use our basic slope formula because derivative is slope. And so you can see my work there, how I'm getting 8 for that answer there. Now, if you look at the units, you did milligrams per square centimeter divided by centimeters, all right, when you did that slope formula. So if you have milligrams per centimeter squared, you divide it by centimeters, that's like timesing it by 1 over a centimeter. And so you're going to get milligrams per centimeters cubed for your units, because it does say using the correct units, interpret the meaning of your answer. Now we know a derivative is the rate, like how fast something is changing, okay? So it tells us that this table, this F, is the density of the bacteria population. And so if I'm doing the derivative, that means it's going to be how fast that density of that bacteria population is increasing or decreasing, depending on whether that derivative is positive or negative. Also, it tells us R is centimeters from the center of the Petri dish. So I use the point value, the 2.25, the number value. So at a distance of that, R equals 2.25 centimeters. When we did a derivative, we're finding that's the density of the bacteria population is increasing at that rate. Part B, you're supposed to approximate an integral using a right Riemann sum. Now, normally when I see Riemann sum, I'm just going to have this. I'm going to go 18 times the distance between the 2.5 and 4, plus the 10 times the distance between 2 and 2.5, plus the 6 times the 1, plus the 2 times the 1. But that's if I'm just integrating that f of x or that f of r. But it gives us a little wrench they try to throw at us with this extra r variable on the inside. So we're supposed to approximate this integral. And so if you see what I did, I'm still using that trick that I shared with you, where you find the right Riemann sum without even doing a graph or a table or anything like that. You just get those numbers from your actual table there. But so you got that R in there. So you got this extra piece where you got to times it by that R. This is your R row. So I'm still going to do my right Riemann sum technique, where I'm going to go 18 times it by 1.5 plus 10 times the 0.5 plus 6 times the 1 plus 2 times the 1. But in front of each thing, I got to times it by the R value. So here the radius is 4. So I'm going to go 4 times 18 times the distance between 2.5 and 4. So that's where I'm getting the 4 times the 18 times the 1.5. And I'm just going to continue that down the way. So my R here is going to be 2.5. So I'm starting at the right side, working my way to the left with the right Riemann sum. So here I'm going to go 2.5. And then we're going to go still times 10 times the distance between the 2 and the 2.5, which is 0.5. So there's where I'm getting that. And I did that the entire way down. So that's why I put that R value like in green. It's that extra piece of information to get this 269 pi. They do have on the rubric there, if you forgot that R value, you just did your normal Riemann sum, you would get some sort of credit for that, but you're not going to get the full credit for that. And then you just got to remember to times it by that 2 pi right there. But remember, Riemann sum is technically like with the rectangles and just from the areas of those rectangles. Now for part C, whenever it asks you, is the Riemann sum an over and under estimate, that's when you're going to look at, hey, is this thing increasing or decreasing? So if I look at these values, those values are increasing. So if I have any increasing curve, it doesn't matter the concavity. If it's increasing concave up or increasing concave down, and you're doing a right Riemann sum, which is what we did on letter C. Think about, if you do a right Riemann sum, means you're starting at the right side of this curve. You're going up to your curve, then you draw the height over, up to the curve, draw the height over. So you start at the right and you work your way to the left. So even if you have a graph that's concave down, if it's increasing, you go up to the curve, draw the height over, up to the curve, draw the height over, up to the curve, draw the height over. Notice that all these rectangles are above the actual curve, but they don't want to hear that. They want to hear, hey, it's an overestimate because all the rectangles are above the curve, but they want to hear, is that function increasing or decreasing? And so that's that. There you go. So we're going to put an overestimate since f of r is increasing. The last part, this is a graphing calculator problem. You definitely need the graphing calculator to do this last part here. So we'll review that real quick. But it says the density of the bacteria in the Petri dish is modeled by this function. And it says, what is the value of the K if G of K is equal to the average value? Now remember, average value, that's your integral. That's your 1 over b minus a times the integral from a to b. So I first need to calculate the average value of this function. So I'm going to go 1 over 4 minus 1 times the integral of 1 to 4 of this G of R function. Now I already have this G of R function graphed in my graphing calculator. Okay, it is in there. and it's graphed in there. So that way, when I go ahead and I do this average value, so I'm going to type in like 1/3 first, and then I got my math 9, and then I could do the integral between 1 and 4. And then since I already have that g of r function in there, that's my y1. I'm going to hit alpha trace. There's that g of r function right there. And then that will calculate that average value for me. That's where I'm getting this 9.876. Now, that's not where we're done. It doesn't just say calculate the average value. It wants to know where is g of k equal to that average value. So g of k just means take the k, plug it in for that r right there. So g of k, here's my g of k. And I want to know when is that equivalent to that 9.876. So anytime you have a hard equation to solve here, here's what I did. I moved everything on one side and I set that equal to 0. I let the calculator find that 0 for me. So I'll do that with you real quickly. So there's my g of r. But then I need to do this minus 9.876. Okay, now I'm going to graph that. It's, I always hit zoom 7 when it has trig in the graph. And so it's already in that mode right there. And then one other thing that we can do, your window, sometimes there's more than 1 0. You're only concerned with in between 1 and 4. So I'm going to hit my window button. And I'm going to make my x min 1 and my x max 4 and then graph it. And when I do that, there's only showing one spot where that's equal to 0. So I'm going to let the calculator calculate that 0 for me. And we're going to be done with this problem. So I hit that trace button. I'm going to hit second trace. I'm going to calculate the 0. So I'm going to go down to number 2, hit enter. And on left bound, I got to move it to the left a little bit. Make sure it's to the left of that 0. So below the x-axis, hit enter. Right bound, I got to move it to the right a little bit. Pay attention to that y variable. Make sure that changes sign. I can hit enter. So I sandwich it on each side of that x-axis. And then for the gas, I'm already in that vicinity right there. So I'll just hit enter on that. And that's where we're getting this 2.497 number. Butterflies.